Hello everybody, I'm Skip Elsheimer and welcome to the AV Geeks Lunchtime streaming show where we watch old 16mm films, and that last film was educational film from the 30s about breathing, something we all need to be doing. And surprisingly, sometimes we don't do it. Our human body's kind of messed up that way, in that sometimes under stress we don't breathe as much as we should be. So just a reminder to do that. Jacob, thank you for the coffee right off the bat. Wait a minute, is my microphone? People are saying that my mic's not working. Can you not hear me? No, I should be broadcasting. Anyways, I'm off track. Sorry, William, something's not going on where you can't hear me. Just not too loud. Interesting. Yeah, see, this is going to be one of those podcasts where somebody's going to sit there and read all the comments. Let me boost my levels some. Is that better? Any better? Okay. Anyhow, here we are. It's the end of a not so great year, but it was a great year because we got to hang out together and watch a bunch of 16mm films, which in non-pandemic times was going to be difficult. You know, really, it's something that I would have to kind of carve out time for. And, you know, so the hidden lining to this dark, dark cloud is the fact that we get to spend so much time watching old 16mm films from my collection. And that ultimately is really, really cool. So we watched, according to my count, and not including what we're watching today, we watched 1,220 films. So that's more than 100 films a month. And that's phenomenal. And you guys, most of you were there for the full thing. So thank you for that. We got a lot more to go. You know, we have, at this rate, we have 20 years worth of film to watch. Wow, that's kind of sobering, actually. Man, I have to sit and kind of figure that out. But I'll keep doing it until I can't, until I don't have time to do it. But this is such an important part of our lives, my life, that I just want to keep going. So thank you again. Thank you for the coffee. Thank you for your comments. Thank you for sharing this with other people. Thank you for your eyeballs. I've tried to be very delicate with them, but you know, sometimes it doesn't happen. So today we're going to watch, it's probably going to turn out to be just one film that has two reels, but it's a Lulu. It's a wonderful film. It is part of the Bell Science series. It is About Time. And it's about time that I've shown this film. And it's about time, and that's the title, About Time. So let's go ahead and get started. Enjoy.
The Bell telephone system brings you another of its series of programs on science. Man's effort to understand nature's laws.
It is written, to everything there is a season, and a time to every purpose under heaven.
Time? What is time? When we try to say what it is, it eludes us. Yet man can measure time with the greatest precision. With his instruments, he can stretch it or compress it. What the scientist knows What he hopes to know about time is the fascinating subject we will explore. The idea of time is so much part of our habits that if we're really to look at it or think about it objectively, perhaps we'd better create a new atmosphere of thinking. And for a new atmosphere, suppose we take an imaginary trip into the vast universe of stars and planets, galaxies and meteors. Now, to set the stage for our story about time, suppose we imagine a brand new planet. There. We'll give it a name, Planet Q. And the people there, as we imagine them, will be normal, intelligent people, except for one strange thing. They don't know much about time, and their king would like to set the clock.
Sir, are we ready to set the clock? Very well. Let the clock be set.
Yes, sir. But where will I put the hands?
Well, what time is it? If you don't know, find out.
Yes, sir. On with the story. We'll call it an Earth scope. We'll use it to examine some of the things that people on Earth have found out about time. Come in.
Hello. Say, we've run into a little problem. I wonder if you could answer a question. The king wants to know, what time is it?
Oh, yes, V.
Oh, the correct time. You see, we're setting our clock so that we can do everything on time.
Well, tell him to set it any place he likes.
Thank you. Any place?
That's right. Well, let's see. Suppose we use the Earth scope screen. Bring the Earth into focus. See what time it is down there.
Is that the correct time?
It is for London, England.
But what time is it?
They call it noon. That also happens at what they call midnight.
Well, is midnight before or after noon?
12 hours after or 12 hours before. It all depends.
On what?
Whether you're talking about yesterday or tomorrow.
But they had to start somewhere. How did they go about it?
The rhythms of nature probably gave man his first awareness of time. Man must have observed the recurrence of natural phenomena, the movements of the sun, the moon, and the stars. He noticed that these events in the heavens seemed to coincide with events on Earth. The spring and the rains, the summer growth of leaves, the autumn ripening of fruit. He thought the moon, sun, and stars controlled his crops, This was understandable because to him, the sun, the moon, and the stars were gods. People began studying the heavenly bodies. As they made notes of their changing positions, the science of calendar making began. Almost every civilization labored to devise a workable calendar. Some of them were based on the cycles of the moon, others on the movements of the sun. But none of them came out just right. Even the Gregorian calendar, the one used today, is not perfect.
Wouldn't you think by now they'd have a perfect calendar?
No, it's not so easy. You see, the time it takes the Earth to rotate on its axis is a day, but the time it takes the Earth to revolve around the sun is a year. But a year comes out to 365 days, 5 hours, 48 minutes, and 46 seconds.
Oh.
And the problem is what to do with that leftover fraction of a day. That's why they add an extra day every 4 years. Except, of course, when that year falls at the beginning of a century.
Of course.
But they add the extra day every 4th century.
Of course.
But it's still off 26 seconds a year.
So they call it a calendar, but it's still off 26 seconds a year.
It's very interesting.
I thought so.
And after we get the clock set, we'll get a calendar. But one thing at a time.
Yes, sir.
Just explain to him
That we need to know the time to eat, to sleep, and so forth. Just any time won't do.
Well, early man didn't regulate his habits to a clock. All animals, including man, and plants too, have a built-in time sense.
I didn't know that.
It's long been considered a wonderful phenomenon of nature that plants seem to know when to flower and set their seeds at just the right time. That furry animals have a way of knowing when to change to their heavy coats before the first cold winds of winter. That birds, by some instinct, know just the right time to set out on their long migrations and always bear their young in a season favorable for survival. It was once commonly supposed that these seasonal occurrences are triggered by changes in temperature. But investigations have shown that plants and animals depend mostly on timing mechanisms within themselves, internal clocks.
Internal clocks?
That's right. Interested?
Yes.
This clock, or biological timer, determines the seasons by the changing lengths of day and night, particularly the periods of darkness.
Darkness?
Yes. Here is Dr. Anton Lang, plant physiologist and director of Earhart Laboratory, who has been experimenting with the timing mechanism of the cocklebur plant. The autumn flowering cocklebur needs about 8½ hours of continuous darkness to flower. As autumn comes, the nights get longer. When they get long enough for the plant's timer to tick off 8½ hours of darkness, the flowering begins.
If the nights get longer, that means the days get shorter. How did they know it wasn't the short days that did it?
Well, they didn't. So they conducted a series of experiments under artificial light. They simulated various proportions of night and day. From these experiments, scientists proved that it is this that the cocklebur plants measure.
And all plants and animals have one of these internal clocks?
Well, some plants and animals have another kind of timing mechanism. This one doesn't measure darkness or any apparent outside influence. It regulates the activities of the plants and animals by time periods alone. Bean plants, for example, have this kind of continuous clock. They raise or lower their leaves without much regard to temperature, light, or darkness. Some animals, like the hamster, also have a continuous clock. The hamster's daily cycle is broken into definite periods. A period for eating, a period for sleeping, a period for exercising. His clock continues to run to regulate his cycles, even though he lives in continuous darkness or continuous light. Practically every kind of living organism seems to have some sort of built-in time sense. Scientists all over the world are trying to find out how internal clocks work. When they do find out, it may mean that the cycles of plants and animals can be controlled, directing their energies into producing more food, more clothing, more shelter.
That's quite incredible. But one thing puzzles me. If man has a built-in clock like those plants and animals, why did he need other clocks?
He found that his internal time sense was not adequate for his needs, which are far more complicated than those of plants and animals. Man had to find other means of measuring intervals of time.
So he invented a clock.
Well, a type of clock. Yes. Actually, he stuck a stick in the ground and told time by the moving shadow. This became the basis of the sundial. The Egyptians developed a clock that measured time with dripping water. And there were other clocks that measured time with flowing sand. None of these early timekeepers could measure small intervals of time with any accuracy. In 1583, Galileo made a discovery which proved to be the first big advance in accurate timekeeping. As he watched a swinging lamp suspended by a long chain in the Cathedral of Pisa, he noticed, by counting his pulse beats, that each swing took the same time. So Galileo proposed using a pendulum as the basis for a clock. To keep the pendulum swinging steadily, the Dutch scientist Christian Huygens devised a mechanism inside a clock that gave the pendulum a little push at the end of each swing. This same mechanism also turned the hands on the clock face, counting the number of swings. It was the world's first pendulum clock, the grandfather of all grandfather clocks, and the grandfather of all our best timing methods. For in order to measure time, you need something that will give you a constantly repeating movement, a rhythm, and then count the movements. The more precisely these movements repeat themselves, the more accurate your measurement of time.
I don't care about bean plants, cockleburrs, and pendulums. Where do we set the clock?
The man in the observatory says we...
I'll find out for myself what he says.
The great Galileo was only 19 when he first observed the regularity of a swinging pendulum. But many years were to pass before he wrote down the idea of using a pendulum to regulate a clock. And it was only after his death that the Dutch astronomer Huygens actually built a clock based on Galileo's youthful reasoning. Nearly 75 years had passed between theory and result. In these critical days, we can't afford to wait so long to put ideas to work. Here at Bell Telephone Laboratories, for instance, many scientists are engaged in pure or basic research, starting with the unknown and ending with knowledge. But one of the Bell system's goals is to put this knowledge to use as soon as possible. The important transistor grew from research by Bell scientists looking into the nature of semiconductor materials. Soon transistors were used in such things as pocket radios. The Bell system's amazingly accurate guidance systems for space vehicles. An experimental helmet radio developed by the Army. and an electronic switching equipment for better telephone service. Other Bell System scientists working with silicon made a discovery leading to the solar battery, thousands of which will be used in satellites to convert the sun's energy to electricity. This will enable telephone calls, data, and television programs to be relayed across oceans via satellites. Again, little time was lost in putting a startling discovery to work. The scientific curiosity of Bell System people, who are always aware that time is important, has resulted in a speedy and vital harvest for communications, industry, and defense. And it is this kind of work that provides continual improvement in your telephone service, unequaled anywhere else in the world.
Quite a piece of machinery, isn't it?
Yes, it is. What is it?
A hairspring and balance wheel of a watch in slow motion.
Oh,
A sort of portable pendulum. Real pendulums work only when they hang straight down, so they're no good for watches or portable clocks. But this mechanism gives a constant rhythm in any position. At each turn of the balance wheel, the escapement mechanism releases the locking of an escapement lever, ticking off the constant rhythm you need to measure time. The first watches were pretty, but not very accurate. Then, as the old world began to expand across the seas, accurate timekeeping became really important. You see, without accurate timepieces, navigation was a problem.
I just checked the sun's position and found out that it's 12 o'clock here. By this watch I've carried ever since we left England a month ago, it's 9 o'clock in Greenwich. So, our position is 3 hours or 45 degrees east of Greenwich.
where does that put us?
In Baghdad, sir.
Baghdad?
Watches just weren't accurate enough to keep exact Greenwich time on a long voyage. In 1761, after years of experimenting, an English clockmaker, John Harrison, developed the first really accurate portable timekeeper. It was off less than 2 minutes after a 5 months voyage. The accuracy of the ship's clock, or chronometer as it's now called, enabled man to navigate any waters and encouraged sailors to explore the seas all over the earth. Although now ships can get Greenwich time by radio, all navigation today still depends on knowing what time it is.
Well, now, that's the same problem we're having, knowing what time it is. I don't suppose you'd care to explain how they set their clocks.
On Earth, I'd be delighted.
Oh, good.
All clocks are set by radio signals. In the Western Hemisphere, these come from the United States Naval Observatory, where signals are broadcast accurate to within 1,000th of a second. From such radio signals broadcast from various observatories,
Where do the radio signals get their time from?
from the official timekeepers, special clocks regulated by quartz crystals.
Quartz crystals? Well, what's wrong with pendulums and those other things?
Balance wheels, they aren't accurate enough. Their rates affected by wear, movement, air currents, and temperature. Quartz crystals are less subject to these influences, but they give us repetitive movement, just like the pendulum and the rotating balance wheel. To the eye, quartz crystals seem inert, but actually, under the influence of an electric current, They vibrate, measuring off tiny and precise slices of time. These vibrations are added up by electronic circuits into seconds, minutes, and hours. Some quartz crystal clocks have a maximum error of 1/100,000th of a second per day.
Well, that's certainly accurate. But if clocks are set by radio signals, and radio signals are set by quartz crystal clocks, how do they set the quartz crystal clocks?
By the master clock, which is the turning Earth itself. Every night when the sky is clear, United States Naval Observatory astronomers photograph stars through a fixed vertical telescope. From this, they determine the precise instant when the observatory passes directly under a particular star. The next night, they note again what time they pass under that particular star. Positions of the multiple exposures on the star plate are then carefully and accurately measured. The information is turned over to the electronic calculator, and the result is the true determination of time. Based on these readings, they're able to find the precise time that it takes the Earth to make one rotation. The official clocks are compared to this, and their rates are calibrated. Come in.
Excuse me, sir, I was just wondering...
Ah, you're just in time. I have come to a decision. We'll set our clock by the Earth, the perfect timekeeper.
Well, not perfect.
What do you mean by that?
The Earth is gradually running down.
Running down? I refuse to accept that.
But it's true. Friction is the main force that's slowing down the Earth.
Where does the Earth get its friction?
From tops. These towers in the Bay of Fundy are good examples. Friction from tide in the shallower seas is gradually slowing down the Earth.
Slowing down? If we can't trust the Earth, what can we trust?
Well, the scientists themselves are not satisfied. Now they're working on an atomic clock. A clock based on the cesium atom has been developed at the National Bureau of Standards in Boulder, Colorado. This clock keeps time by counting motions inside the atom. As the nucleus spins, its axis swings back and forth, and the swings are detected electrically and counted. The motions of atoms are more regular than those of pendulums, balance wheels, the Earth, and even of quartz crystals. And it's likely their regularity will continue as long as matter exists. This clock is believed to have a maximum error of 1 second in 3,000 years.
Well, that's accuracy.
Sir, it occurs to me...
Yeah?
Well, I don't think it would make much difference to anybody if they did lose a second or two now and then.
Oh, everyone depends on accurate timing, they're aware of it or not. For example, with quartz crystals, it's the precisely controlled number of vibrations per second that determines the kilocycle and megacycle channels used in broadcasting, television, in multiplex, where many messages travel a single cable or travel a radio relay beam. Accurate timing of electrical impulses is the heart of all communication systems. An even greater accuracy in timing is needed by scientists who are constantly trying to get a more complete and accurate understanding of the physical universe. And today, the quantity that can be measured more accurately than anything else is time.
Well, I suppose such accuracy is important to scientists and engineers.
But still, 1 little second doesn't seem so important. Really?
Oh, a second is important. Take a look.
9 3/10 seconds.
What kind of a clock was that?
A stopwatch. It measures intervals of time down to 1/10 of a second. Of course, it's not very practical when you're trying to measure 1/millionth of a second.
But who'd want to measure 1/millionth of a second?
Scientists, engineers, technicians, anyone who deals with things moving at high speed.
What kind of a clock would they use for that?
Usually a cathode ray oscilloscope.
Never heard of it.
Basically, it's much like a TV picture tube, but it's used differently. The beam of electrons sweeps across the screen over and over again in the same track. Now, if we connect, say, a microphone, sound will jog the beam and make a jog in the trace, like this. The ticks of a watch put time markers on the sweep, 5 to the second. When we speed up the sweep, the time between ticks is stretched out to full screen. Speeding up the sweep still more, and using an electronic timer, we can put on markers of 1/100th of a second or less, and measure the speed of a bullet as it cuts two wires only a foot apart. Let's take another look and stop there. The interval between the two vertical lines we've drawn here represents the time it took for the bullet to break the two wires.
How long was that?
1/1000th of a second. That's really quite a long time. A radar scope with even faster sweeps tells how long it takes for a radar signal to strike an object and bounce back. That tells you your distance from the object. Or you can time signals from 3 LORAN stations operated by the United States Coast Guard. By comparing them, adjusting the traces so they will coincide, know your exact position. By putting markers on a very fast sweep, scientists find it easy to measure intervals of 1/1000th of a second.
Well, that's not too bad, is it?
Do you have any idea how short a time that is?
Do you?
Frankly, I don't.
Well, 1/1000th of a second has the same relationship to 1 second as 1 second has to 35 years.
1 second to 35 years. Yes. Now I see how small that figure is.
And even 1/1000th of a second is long compared to the much shorter times that scientists have to deal with. Although the atomic world that makes up this drop of water is still hidden from the eyes of man, we know a good deal about how these bits of matter behave, how they move, and in how short a time. In this drop of water, there's a vast number of atoms in constant motion, and just one of these atoms will have 10,000 collisions in 1/1000th of a second. And in the time between each of these collisions, the outside electrons of the atoms would go around 100 times. And in the time it takes an outside electron to go around just once, the inside electrons would go around 100 times. And in the time it takes the inside electron to go around just once, the particles in the nucleus of the atom would vibrate 100,000 times. These are the time scientists must try to measure.
All right. Where am I? Hey. Thank you, Sam Monty. Thank you, William, for the coffee. That is much appreciated. We run on coffee here at AV Geeks, and you can donate at ko-fi.com/avgeeks or buymeacoffee.com/avgeeks. I like, speaking of advertisements, I like the fact that there was a AT&T advertisement snuck into that film. I think About Time came out later, in later iterations. The first one of the Bell Science series was Our Mr. Sun. and then there was other ones after that. And this feels like this was a little bit later, but it has Richard Deacon in it. Richard Deacon, man, it's my favorite character actor on the Dick Van Dyke Show, and also on Leave It to Beaver. And he shows up on The Twilight Zone. He shows up lots of places. He's really phenomenal character actor. But anyways, so I have to rewind this film. So, yeah, so I'm going to rewind this, and in the meantime, I'm going to show you something that, that we just haven't seen in a while. So, just because I haven't found anything that's appropriate, we'll just watch this as I rewind. All right, enjoy.
What, may I ask, is a dear little cupcake like you doing with nasty old school books? My dear child, we haven't had school or books in ages.
No school? Really?
Why don't you get rid of that school book? You can drop them in here.
It'll get all burned up in there.
Well, of course it will, dear child. And so it should. Books tamper with man's basic, natural ignorance. Now, what could be worse than that?
But I can't burn this book. It's school property.
Nonsense! Apple sugar. You just need to get into the mood.
Books are not where it's at, teaching you how to spell cat. I know you'd rather play, so why don't you throw all your books away? Books are made for burning, the fire is already yearning to put an end to any learning.
1, 3, 5, 9, throw them in, the fire's dry.
Put the books in the fire, see the flames growing higher. Burning books is our heart's desire.
2, 4, 6, 8, time to incinerate.
Books will not make you wise, and reading's bad for your eyes. I am sure you agree, so why don't you give all your books to me? Books are made for burning, fire is already yearning to put an end to any learning.
This one here is very good about a man named Robin Hood.
Put the books in the fire, see the flames growing higher. Burning books is our heart's desire.
Though I never liked Tom Sawyer, I won't be a book destroyer.
Books can only confuse, teaching you things you can't use. You should listen to me. Burning your books will set your mind free.
Books are made for burning, fire is already yearning to put an end to any learning. Put the books in the fire, see the flames growing higher. Burning books is our heart's desire. Books are made for burning, fire is already yearning to put an end to any learning. No, stop!
Still rewinding. All right. So when I used to do, before the pandemic, I would do like a monthly live streaming show, like on a Sunday. And so I would show everything from film, and I would basically be talking while the film was rewinding, which some people were annoyed by that. So that's why I kind of bounce back and forth between showing something I've already digitized and showing another film. So here's About Time Reel 2. Here are some things. This is called film leader. This is at the beginning of a film so that you have room to thread. And also this is a great place if you messed up in your threading and you're shredding film. It's better to shred leader than it is actual film. This is yellow, and you can tell it's got a little warp to it, so it's beginning to go a little shrinky. Here's a sticker, which you can't see because it's all blown out. Electronically inspected. Alright, we're threading up, going through the sound head, which on the telecine is actually before the visual gate, which is most projectors have it after, because the audio is like 26 frames behind the visual frame. Let's see, what else? Need some tension here. This machine uses tension to move the film through instead of using a little claw. Projectors usually have a little claw that reaches, goes in, finds a sprocket hole, pulls it down, rather than pulls it down. This doesn't use that, but it does use a little wheel with sprockets on it to determine where the frame is. So if it's torn sprockets, or if it's splicey, or if it's shrunken, it'll roll, and that's why you see that. All right, so here we are back. It's about time, reel 2. Enjoy.
It's all been very interesting. And now if you'd just tell us what...
Wait a minute. I have a question. You have been splitting time smaller and smaller. Now, is there any limit to how small time can be split?
If there is such a limit, it would be shorter than the time it takes light, which is the fastest thing we know, to go across the smallest piece of matter, which is an atomic particle. This would be approximately 1/millionth of a billionth of a billionth of a second.
Well, they wouldn't want to split it any smaller than that.
Certainly they would. If they could. Wouldn't they?
Yes, if they could. You see, if there is a limit to how small time can be split, it would mean that time is not a continuous flow, but is made up of little pieces.
Little pieces of time. It's unbelievable.
That's because our feeling of time is limited. We can grasp only those intervals we're familiar with. Seconds at one end of the scale, hours, days, months, and at the other end, the number of years in a lifetime. This is a very small range in the middle of the vast scale of time. The infinitesimal fractions of seconds at one end and the billions of years at the other. We say that the age of the Earth is 4.5 billion years, but how long is that? Let's consider the life of the Earth in terms of what went on, what happened, what changed. Since it's difficult to relate our feeling of time to large numbers, let's squeeze the age of the Earth into one 24-hour day. We begin at midnight, 4.5 billion years ago. It's a long time, say 2 o'clock in the afternoon, before any life at all appears on the Earth. At 7 p.m., life begins leaving remains in the form of fossils. Dinosaurs develop at 11 p.m. Only 1 hour left to go in our Earth day, And now, at just 2 seconds before midnight, the human species first appears on Earth. In the last 1/10 of a second, the entire 6,000 years of civilization since the early Mesopotamians and ancient Egyptians takes place. And in the last 1,000th of a second before midnight, there are the 2 world wars.
But there's one thing that bothers me. If people weren't even around most of that time, how do they know what went on and when?
Perhaps a geologist should tell you about it. This is Dr. Gerald J. Wasserberg.
The events in our natural history and the times at which they occurred can all be told from rocks. By examining the fossils, the minerals, the makeup of the rocks, we can tell what happened and the sequence in which these events happened. By using radioactive elements as our clocks, we can answer the question, when did certain events happen? We know, for example, that in 4.5 billion years, 1/2 of the uranium in a rock turns into lead. By measuring the proportions of uranium and lead in a given rock, we can figure how long it took for that amount of lead to form. This gives us the date at which the rock solidified. In this way, we have been gathering information on the age of the Earth, its eras, and its epochs.
They see all that in rocks?
Yes, rocks hold the secret of our past. They're the only history of the Earth. It's all there in the rocks, waiting for man to discover. Some places, nature has given man an opportunity to see the changes that have taken place over vast periods of time by exposing a sequence of layers, preserving for us a long record of Earth history. Records that show there were once deep waterways where mountains now stand, large land masses that have been lost to the seas, and the Earth is still changing. The same forces that have changed the face of the Earth in the past are still at work. Wind, rain, glaciers, look in the eons to come. If the Earth has a past of 4.5 billion years, what is its future? We can only guess, but the vast time of the past is small compared to the far greater expanse of time that is the future.
We've gone from a millionth of a billionth of a billionth of a second to billions of years.
Well, that certainly covers time.
Do you know what I like about time? It has order. It has mathematical precision. One can almost see time evenly flowing throughout the universe.
Very interesting that you should describe time that way. That idea of time was accepted as scientific truth on Earth.
Very good thinking, sir.
Accepted, that is, until the beginning of the 20th century.
Just what do you mean by that?
Time is no longer considered absolute. It is not the same everywhere.
You mean that the same time here is not the same time there, and that the same time is not flowing everywhere?
No, I'm afraid it isn't. How does that look to you?
They're moving too fast.
How does it look now?
Too slow.
You mean that one group's moving slower and the other's moving faster than we are?
Well, yes, moving normally, but they're not.
But if you were with those people, moving at their rate of speed, either fast or slow, it would seem normal to you.
And I couldn't tell?
Not if everything conformed to that rate. The speed an object falls, the water pours, the speed you talk and think. Look at those people moving at different time rates. They look peculiar to us. They look peculiar to each other. And to them, people moving in our time rate would look peculiar.
Well, that was an interesting demonstration, but I still can't believe that in real life, time could flow at different rates.
Well, scientists have found that time rates are actually different under certain circumstances.
Well, under what circumstances?
Well, for one, the faster anything moves, the slower the time rate for everything connected with it.
You'd better tell me that again.
All right. Just imagine people traveling in a spaceship at almost the speed of light. They'd be living in a much slower time rate than we are.
They would, eh? Well, how did they figure that out?
It all began with a famous experiment made back in 1887 by two American physicists, A.A. Michelson and E.W. Morley. They wanted to measure how fast the Earth is moving through space. So they set up an experiment based on a simple principle we all know well from everyday experience.
We do.
Well, let me show you. Now, suppose we're in a moving car. A train going in the same direction passes us much more slowly than it does when we're going in opposite directions. In fact, the actual passing speed is simply the addition or subtraction of our speeds. It was this principle that Michelson and Morley tried to use in their experiment. Only instead of sitting in a moving car, they sat in their laboratory on the moving Earth. And instead of a train, they used light. By comparing the speed of the light in various directions, they hoped to measure the speed of the Earth.
Well, what happened?
There was no effect. The light seemed to travel in the same speed no matter which direction it was going. In other words, it looked as if the Earth is standing still.
That's impossible, isn't it? I thought it goes around the sun.
Yes, they've known that for 400 years. So scientists went right on making more experiments to detect the motion of the Earth through space, but without any effect.
How did they explain their way out of that one?
Among those who proposed explanations was a young clerk in the Swiss patent office named Albert Einstein. He said, of course the Earth is moving, but the laws of nature must be so constituted that there's no way to detect it or to prove you're moving without comparing or relating to something outside that isn't moving along with you. This is the principle of relativity.
Einstein's theory of relativity.
The first part of his theory, it's really not so hard to believe. For example, in a plane flying at a uniform speed without any bumps or turns, you can't tell you're moving without looking out of the window.
So, in order for Michelson and Morley not to be able to tell the Earth was moving, the light had to travel the same speed in either direction.
And that was the second part of Einstein's theory. He said that light would always be observed to travel at the same speed, no matter how fast or in what direction you were going.
You mean, if I were in a very fast spaceship, a beam of light would seem to pass me just as fast as it would you on the ground?
That's right. Sounds impossible, doesn't it? But Einstein explained it by pointing out that the only possible way that two people traveling at different speeds can both measure the speed of light the same is that their measuring devices have become different because of the difference in their speeds. And so they have different senses of time and space. For example, if you were in a spaceship, to me on the ground, your clock would seem to be running slower than mine.
Let's try it, huh?
All right. With some simple animation, let's see why the clock in a spaceship traveling near the speed of light and the clock on the Earth measure time differently. Now here's a simple clock, a hollow transparent rod, a mirror on each end, and a beam of light bouncing from one end to the other. The beeps tick off regular intervals, same as any clock. Now we have two of them. One is put in the spaceship and one kept on the ground. To the man on Earth, his clock continues to run at the same rate. But when he looks at the spaceship going by, the action of the light in that clock looks like this.
I think I see what's happening.
Perhaps it'll be even clearer in slow motion. Because the spaceship is moving past the Earthman, the light appears to him to travel diagonally to get from one end of the clock to the other. Because the light has to go further, it takes longer between ticks. And from the Earthman's point of view, the spaceman's clock is running slower.
The man in the spaceship must think his clock is crazy.
I would certainly think so.
Well, let's see. Inside the speeding spaceship, the spaceman looks at his clock. It seems perfectly normal to him, just like it did on Earth. His sense of time is different. Everything is changed proportionately, so that no change is apparent.
Well, then, if he's also taken along a wristwatch or an atom clock, they would have had to slow down too.
Yes, all sorts of strange things would have had to happen. Weights would increase. Lengths would change. All in perfect proportion, so that he wouldn't notice any change, and so that everything would seem perfectly normal.
But everything seemed normal?
Remember the first part of Einstein's guess? The principle of relativity? The laws of nature are so constituted that you can't tell you're moving without relating to something that isn't moving along with you. Then everything in the spaceship must seem perfectly normal, or else the spaceman could tell he was moving. With our light clock, it's easy to see how this effect increases as your speed approaches the speed of light. It's the same with everything in motion. But in our normal lives, we never get anywhere near speeds great enough to show this effect.
With our talk about that spaceship, is it possible that people may someday travel near the speed of light?
At the moment, it's pretty remote. But based on Einstein's theory, it's fun to conjecture what would happen. Here is a story of identical twins living in the Einsteinian future. Our twins, Peter and Paul, they're having an argument over who's to have the honor of being the first Earthman to travel to the distant star, Arcturus, and back.
I want you to have the honor. No, you deserve it. See you in 60 years.
Although Peter was 83, he didn't want to miss his brother's moment of glory. Yes, compared to his brother, Paul was still a young man.
He doesn't look 83.
He isn't. Traveling near the speed of light, he aged less.
Oh, yes. Time slowed down.
That's right. The closer he came to the speed of light, the more Paul's heartbeats, with their periodic motion measuring time, would slow down, along with his rate of breathing and other body processes. Paul would notice, though, because his watch would slow down to the same degree.
How do you know that Einstein guessed right, and his theory is really true?
Well, let's ask a physicist. Dr. Richard Feynman of the California Institute of Technology.
In the laboratory, we can get atomic particles to go nearly at the speed of light, and, so far, all the effects predicted by Einstein show up. For example, particles which are unstable and disintegrate do last longer when they're moving than when they're standing still. Einstein's theory of relativity has radically transformed man's picture of the universe. It has upset our traditional ideas about time and space. And someday we may upset them once again because we're still learning. What determines the direction of time? What distinguishes past from future? And what exactly
is the present. Is now the same for everyone?
Ask me for anything you like, said Napoleon, except time. Today, in our fast-moving world, your telephone gives you this priceless commodity which were Napoleon's to give. The telephone is the speediest of all messengers, giving time by saving it. For instance, it's easy and convenient to shop by phone when time or duties keep you at home. At your instant beck and call, department stores. The plumber. The druggist. A friend across town or far away. And in business as well, the telephone is a speedy messenger, making miles meaningless, shortening days to minutes, getting things done more easily, getting things made fast and efficiently, doing business, buying and selling, supplying and distributing to all parts of the country. Over its teletypewriter networks, the Bell system has long been a speedy courier of written words as well as spoken words. National and international news stories are flashed over teletypewriter lines to newspapers and to radio and television stations across the land. And the remarkable new Bell system data phone service provides even faster and more flexible business communications. Computer or business machine language is sent over long-distance circuits at high speed to other business machines by Bell System Dataphone. In all these ways, the telephone serves as speediest of messengers for business and for the home, giving time by saving time. Ask me for anything your telephone might say, including time.
Doctor, is now the same for everyone?
No.
I was afraid of that.
Well, thanks for the use of the planet.
Oh, wait, please. You're not going to leave me now, are you? I mean, we've gone all the way from shadow on the ground to
sundials and pendulums,
and from atomic clocks
to suns, moons,
stars,
from time that was fixed
to time that is relative.
We've come a long way.
Yes, but now I have more questions than ever.
Good. The more we learn, the more questions we have. In the beginning, you had only one question. What time is it?
That's right. Well, where do I set the hands of the clock?
Oh, that. You can set them any place you want.
You mean because I'm the king?
No. Wherever you decide to set a clock in the beginning is more or less arbitrary. However, once you've set it, that becomes your time, and all your clocks must be synchronized.
Well, thank you.
Now we can set our clock. Sir?
Well, for our purpose, that sort of winds up the story of Planet Q. But the story of time is just beginning. Stretching before us are who knows what complexities, perplexities, mysteries. How did time start? We don't know. Did the universe begin with a big bang 10 billion years ago? Some physicists and astronomers think so. But others ask the question, did the universe even have a beginning? Or has it been going on forever? Will it ever end? some 20 billion years from now, when our sun burns itself out and explodes into oblivion, will time stop? Or will we just sit cooler and cooler, longer and longer, without light, without warmth, in the fathomless depths of space? These are questions which baffle astrophysicists, cosmologists, many men of science. Men whose minds and imaginations are even now uncovering clues to the mystery of time, which has perplexed mankind for centuries. What time is it? The answer may be phrased in terms of molecular action, the laws of nature. But more directly, what time is it is a question of our everyday lives, the contraction of our lungs, the beating of our hearts, the measure.
I can check that gear in a minute, so don't touch anything, okay? Hey! Get down from there! Now! Hey! Turn it over! What if it bumped that control by accident? You'd be mincemeat by now. What have I told you? You don't work on equipment when the engine's running.
Well, I told him not to touch anything. All right, I guess I wasn't thinking.
You weren't thinking? You mean you'll work on engines and machinery and not think of your own personal safety? Here. Shake hands with danger.
Shake hands with danger. Meet a man you ought to know. I used to laugh at safety. Now they call me Three-Fingered Joe. I was young and feisty, never did things by the book. Just let me get my toolbox and I'll take myself a look. I climbed up on a dozier with my mechanic's pride. Said, you can keep it running, friend, while I poke around inside. Shake hands with danger, meet a guy you ought to know. I used to laugh at safety, now they call me Three-Fingered Joe. Although I learned a lesson, I forgot it soon enough. The nicks and burns and scratches showed the young ones I was tough. Till another morning I was grinding on some steel. My other hand got careless and fed my skin into the wheel. Shake hands with danger, step right up and say hello. Grinding wheels and metal are what made me Three-Fingered Joe. I've seen mechanics burning and I've seen them take a fall just to save themselves a minute. I've seen them lose it all. I've watched them courting trouble, seen them take a chance and lose. They get careless for a moment and spend a lifetime with the blues. Shake hands with danger.
around inside. Shake hands with danger. Walk around inside. Shake hands with danger. Walk around inside. Shake hands with danger. Walk around inside. Walk around inside. Shake hands with danger. Walk around inside.
Shake hands with danger and some friends I used to know. Compared to them, I'm lucky to be just Three-Finger Joe.
So I don't know if Betty White has passed or not. She's great. She rocks. She died a great, amazing person. If she didn't die, then shame on whoever perpetuated that misinformation. But what I do know is that we watched 1,222 films this year. And we'll be back next Monday, this Monday, coming up, and we'll watch even more. And maybe we'll try to figure out a way to squeeze in, I don't know, even more films next year. And I hope that you will be there to join us. It means a lot that you guys have tuned in all this time to see your friendly names and your comments. I started doing this like last year because I was frustrated with not being able to show my films live. And it turns out that this is really important to me. I hope that you enjoy it, and I hope that you find value in it. And and also we watch some pretty goofy stuff, so there's some stuff that's not valuable and some stuff that is horrible. But I appreciate your help, your support, your eyeballs, and we will see you again next year. Everybody take care of yourselves. Please rewind, love each other, love yourself, and goofy stuff like that. Take care. Bye.